I'm Yifeng Teng from the University of Wisconsin-Madison, and today I'm going to talk about the paper Manual Size Complexity and Revenue Continuity of by Many Mechanisms. This is joint work with Shuchi, Chawla, and Christos, Tzamos. Okay, so we consider a combinatorial market where a seller has n different items to sell to a single buyer. The buyer's private value is unknown to the seller, but is drawn from a distribution that is publicly known. And the buyer will have different values for each set of items. And here we do not make any assumption to the structure of the valuation function, but only assume it's monotone. That is, adding any item to a set would not reduce the buyer's value for that set. So although the single buyer mechanism can be very complicated, by taxation principle, any mechanism is equivalent to a menu of choices. The seller lists a menu of options to the buyer where each menu entry is an item allocation and its corresponding price. The buyer chooses the single menu entry such that she can get the maximum utility. And the menu entry can be a price for a single item, or price for bundles of items, or a price for some lottery of items where after purchasing the lottery, you can only get some of the items with some probability. And the number of options on the menu is called the menu size of the mechanism, which was introduced in a seminal paper by Hart and Nissan. It is known that the optimal multi-item mechanism can be complicated compared to single item setting. The optimal single item mechanism is just a positive pricing mechanism, and thus it's deterministic and has menu size 1. However, in multi-item setting, even when there are only 2 items, options with a random allocation on the menu are usually necessary. And infinite number of menu entries may be needed to get the optimal revenue, even in a very simple setting like selling 2 items to an additive buyer with independent item values. And furthermore, when the buyer has correlated item values, the mechanism with finite menu size cannot get any tiny fraction of optimal revenue. In this work, we study the by many mechanisms that allow the buyer to interact with the mechanism for multiple times. And this is a very common assumption in both digital and physical markets in the real world, and reasonable and natural constraint to the classic what we call by one mechanisms that only allow the buyer to participate in the mechanism for once. Okay. So here is an example of the multi-item mechanism illustrating the difference between by one and by many mechanisms. Suppose that the buyer wants to purchase a sandwich and a drink, and her value for the sandwich drink bundle is much, much higher than her value for the individual items. And if the mechanism only allows the buyer to purchase one menu option, then the buyer will purchase the third menu option and pay a lot of money, since this is the only way to get both items. However, in a mechanism where the buyer can purchase multiple menu options, the buyer can have the following adaptive strategy. Firstly, the buyer comes and repeatedly purchases the first menu option until she gets the sandwich, then adaptively purchase the second menu option until she gets the drink. The buyer pays the total price of all the realized options, and it is only $16 in expectation. In previous years EC, we showed that the optimal by many mechanisms can always be approximated in revenue by simple mechanisms. And in particular, item pricing gives an O log n approximation to the optimal by many revenue. So such results does not require any assumption on the value distribution D that it can be an arbitrarily correlated distribution over an arbitrary valuation functions. This contrasts the results for by-one mechanisms where no mechanism with finite manual size can get a finite approximation in revenue. And this brings up many open questions. For example, do by-many mechanisms have other nice properties that by-one mechanisms don't? And can we hope to obtain some better approximation ratios, for example, constant factor approximation to the optimal by-many revenue? And in this work, we'll address a few such directions. The first direction we study is that how large does the maximum manual size have to be to obtain a near optimal revenue. So recall that this is infinite for by-one mechanisms, but we will show that it is only finite for by-many mechanisms. So the second direction we study has to do with the revenue monotonicity. And I will define it shortly. And it is well known that by-one mechanisms are not revenue monotone, while by-many mechanisms are also not revenue monotone. We'll show that they satisfy a sort of continuity in revenue. Okay, so let's start with the first problem. So for by-many mechanisms, as we have seen that item pricing gives a log n approximation in revenue. So how can we realize item pricing? We only need to post the manual of size n with the price for each item, and the buyer can come to purchase any silo options. So a natural question is that what is the manual size needed for getting near optimal revenue? For by-one mechanisms, as we mentioned before, it's known that no mechanism with finite manual size can achieve this. And the finite manual size is only known to be enough for getting near optimal revenue when the buyer has specific value structure, such as sub-additive valued buyer with independent item values. So, however, in this paper, we show that a finite manual size is enough for getting near optimal revenue obtained by many mechanisms. And formally, the theorem is stated as follows, that for any distribution over any valuation function, it is possible to find by many mechanisms with a finite manual size, such that manual size only depends on the number of items and epsilon. And this mechanism can get 1 minus epsilon approximation to the optimal revenue obtained by many mechanisms. In this theorem, the manual size needed, the function f, is a double exponential of the number of items. So this may seem like a super large value, but actually we can prove the following tightness result by showing that no mechanism with description complexity, sub-double exponential in n, can get better than log n approximation in revenue, even when the distribution is over some XOS valuation functions. So the dependency on n is essentially tight. So to prove this theorem, we first have the following key technical observation that does not hold for by-one mechanisms. So for any by-many mechanism, if two options have similar allocation for every set of items, they must have similar prices. So this is because that if the allocation of set S in allocation X is at most 1 plus delta times the allocation of S in X prime, we can simulate purchasing X with purchasing X prime by first purchase one copy of X prime, then with probability delta purchase X prime again. And this way we get an allocation that dominates X. So given this observation, the high-level idea of how to prove the theorem is that we can discretize the allocations in the menu to the power of 1 plus delta for each set. And the price of any allocation does not change much. So after the discretization, the manual size is going to be finite. And such discretization of allocations is actually always not possible in by-one mechanisms. And the second property we want to explore is the revenue monotonicity. So we want to understand the following question, that when the buyer's values for each set of items increases, how does the optimal revenue change? So when selling to a single item, the revenue increases since the posted pricing mechanism is optimal, and the same mechanism has increasing revenue for the perturbed distribution. And for the multi-item setting, a surprising result by Hart and Rennie shows that the optimal revenue obtained by buy-one mechanism will decrease when the values increase, even for a buyer that is additive over two independent items. And such a phenomenon is called the revenue non-monotonicity. And unfortunately, we show in our paper that such non-monotonicity can also exist by many mechanisms. So given this observation, we want to know a weaker result. That if the valuations increase only slightly, so how much can the optimal revenue decrease? And more generally, we ask the question that when the buyer's value is slightly perturbed multiplicatively by a factor of 1 plus minus epsilon, how much can the optimal revenue change? So in a single item case, the same way as before, the optimal revenue only changes slightly for the simple posted pricing mechanism. For a multi-item case, a surprising result from an example in Tzamos et al.'s EC paper last year is that the revenue obtained by optimal buy-one mechanism can change significantly after the value gets perturbed multiplicatively. And it is even possible that before the perturbation, the optimal revenue is infinite, while the revenue after the perturbation is only finite. So revenue continuity for buy-one mechanism only holds when we use the Whittaker perturbation model when the values are perturbed additively, and there is another EC paper working on that this year. However, in this work, we show that such revenue non-continuity doesn't happen to by many mechanisms. And in particular, for any distribution over any valuation functions, the revenue obtained by optimal by many mechanisms does not change much under any multiplicative perturbation of the value distribution. The revenue may decrease only by a factor of poly n and epsilon, and we can observe that this dependency on n is necessary and cannot get removed. So we will take an example with epsilon equals 1/2, which means that the value of the average buyer type will decrease by a factor of 1/2 to show that when the number of items is large, the revenue can decrease a lot after perturbation. Okay, so consider the original distribution D as shown here. That's with probability 2 to the minus k, the buyer has a value Vk, that is a unit demand valuation function, as shown in the table. And her value for item k is 2 to the k plus 1, while her values for the rest of the items are 2 to the k. So what is the revenue we can get from this distribution? So we'll consider the item pricing that has price 2 to the I for each item. And for any buyer of type K, her utility of purchasing item K is 2 to the K, while her utility of purchasing any other item is strictly less. So this means that her payment is going to be 2 to the K, and the expected payment over all buyer types is going to be N. So we consider following multiplicative perturbation. That's the value of item K for each buyer type Vk decreases by 1/2. So this way, the buyer, so for each buyer type, it will have the same value for all of the items. And for such unit demand buyer, it just becomes a single parameter setting, and the optimal mechanism is just to pose a price to the ground bundle of the items. And the optimal revenue is only a constant. So this means that after value get perturbed multiplicatively by 1/2, the revenue obtained by many mechanisms can reduce by a large factor that depends on n. And such example can be generalized to arbitrary epsilon, saying that the by many revenue after perturbation can decrease by a factor of epsilon times n. So this shows the dependency of n is necessary in the theorem 3. Okay, so now we'll give a sketch of how we can prove the revenue continuity result. So we start with the optimum revenue for the original distribution. And we will construct a mechanism for the distribution d prime after perturbation such that the price of each option in the original mechanism is discounted by a factor that is close to 1. For any buyer that purchased a lottery with xi in the original mechanism, she may purchase a different manual option with allocation xj after her value is perturbed in the new mechanism. So if the buyer's payment in the new mechanism is always close to her payment for every buyer type, then the expected revenue is also close and the theorem holds. The problem is that this may not always be the case, but for by many mechanisms, we are able to show that the values from the buyers that's such that the above inequality doesn't hold, only contribute a tiny fraction of the total revenue. So this means that the revenue of the new mechanism under distribution after perturbation is close to the optimum revenue obtained by the by many mechanism under the original distribution. And this proves the continuity result. Okay, so now I would like to conclude my talk. And in this talk, we show that the by many mechanisms have many nice properties that by one mechanisms don't have. For example, finite manual size is enough to get a near optimal revenue, and the revenue continuity property for the buyer's value perturbed multiplicative. And the two results do not assume any structure or independence in the value distribution. And here are some other directions on understanding by one and by many mechanisms. For example, can we find some other properties that separate by one and by many mechanisms? And can we get better approximation results for by many mechanisms in special cases? For example, selling the revenue approximation for an additive buyer with independent item value.